That clock right there, that's your official clock.
That's the official clock. Okay, so how was the food?
Good.
Okay, so do I have enough time for one quick joke?
You got the clock, not me.
Okay, well, it hasn't flipped over yet.
24 sponsors.
24 sponsors. Okay, that's not the joke, though. This is a food-related joke. What did the astronaut say when he ate his dinner on the moon?
What did the astronaut say, Al?
Time's up. Do you have
The,
any?
the food was good, but it lacked atmosphere.
And don't play
Okay, well, the clock just flipped over, so we're on time.
Thank you, sorry.
So I would like to introduce our speaker here, Dr. LeeCarkner. He's a professor of physics and astronomy at Augustana College, Rock Island, and he's the director of the John Deere Planetarium, and he's a member of our club. So that's probably the most important, thing. Anyway, so I think, and then later we're going to be making a trip over there. So I guess with that, I am going to see if I can work the magic here. Okay, we're going to be talking. Your talk is a relativistic century, Eddington, Einstein, and the Great Eclipse. And I'm going to see if I can get it going. Did it work?
Is my mic working?
I'm going to shut this. Did you turn that one on? I'm going to shut this one off. This one seems to override it. Okay.
Okay, how about now?
Yeah.
All right, thank you. Well, thank you all for that introduction. I am LeeCarkner. I am going to be talking a little bit about the relativistic century. When we announced this conference, I realized that it's very close to the 100th anniversary of Eddington's eclipse observations. So I chose that as a subject for my talk. But this event was more than just confirming one theory. In the early 20th century, modern physics was this crazy new stuff, and to a lot of people it didn't make a lot of sense. And it was weird how all these things that underlie our reality were so non-intuitive. And so having empirical evidence for it was a really big deal. So I want to talk a little bit about the event itself, but also the way people reacted to it in the 20th century. I'm inspired a little bit by Paul Johnson's History of the 20th Century Modern Times, which is sort of a history of the 20th century. But Johnson starts the book, he begins with this event. The first sentence in his book is, "The modern world began on 29 May 1919, when photographs of the solar eclipse confirmed the truth of a new theory of the universe." So he frames his entire history of the 20th century with this event. So I wanted to talk about the effect that it had. Well, let's start with the 20th century. In 1901, Queen Victoria died, ending the Victorian age. Her son became King Edward VII. That was the Edwardian era, the early 20th century. And it was a time of stability and prosperity. There hadn't been a major war in Europe in 100 years. These European countries were very powerful. The Industrial Revolution had completely changed these societies. There was a global network of trade. It was a time when there was a lot of globalization, a lot of technology, a lot of prosperity, a lot of stability. And this picture kind of illustrates symbolically. This is the King of Britain. This is Edward VIII, Edward VII. And this is his nephew, who was Kaiser Wilhelm, the Emperor of Germany. Wilhelm's grandmother was Queen Victoria. Many of the heads of Europe were all related to each other. They were all tied together by blood. So that was kind of symbolic of how stable things were. But of course it wasn't, right? This was an illusion. The world wasn't stable at all. In 1914, it all came crashing to a halt. All these nations, with all their prosperity and all their wealth, went to war with each other and essentially built a giant killing machine in the middle of Europe and just fed millions and millions of men into it until they collapsed from exhaustion. this was a shocking thing. This wasn't supposed to happen. Everything was kind of supposed to be set, supposed to be solved, and things were supposed to be stable, but they weren't. Rudyard Kipling wrote an epitaph for the dead in the war in 1919, the year we're talking about. My son was killed while laughing at some jest. I knew what it was, and it might serve me in a time when jests are few. He encouraged his son to go off and fight, and his son was killed at the Battle of Loos and was not seen again. But this was an epitaph in some sense, not just for his son or for the British war dead. It was an epitaph for the whole structure of society, which seems like it just fell apart. Well, in the year 1919, people didn't know what to do at the end of the war. How were we supposed to structure society? The ideas we had before weren't working. So people came up with new ideas. In Russia, the Bolsheviks led an armed revolution and took over the country of Russia and founded the Soviet Union. But communism wasn't just for one country, it was supposed to spread throughout the world. And in 1919 in Moscow, they had the Third Communist International, where they vowed to spread communism all over the world. This old idea that maybe you could convince people through parliamentary elections, they said, we're not going to do that anymore. We're going to advocate armed uprising all over the globe. This was a new idea that was supposed to replace the old ideas. But in some sense, it was very similar to the old ideas. If you make a structure big enough and powerful enough, if you make the state powerful enough, then that will solve all our trouble. Also in 1919 in Italy, Benito Mussolini's fascist organization released the Fascist Manifesto, laying out their program for how to go into the future, to diminish the power of the king and the nobility of the church, and to build a new fascist government. Again, built on the same idea. If you believe strongly enough, if you make the state powerful enough, maybe we can solve our problems. So this was a time of great upheaval, when the old ideas were being thrown out, and new ideas were coming in, and it wasn't clear what you were supposed to believe in, or how you were supposed to believe in. So into this world comes Albert Einstein. Einstein was born in Germany. He was from a Jewish family. He went to college in Switzerland, in the Polytechnic in Zurich. He was a good student. He was smart. He got good grades. Then he graduated from college. What do you do when you graduate from college with your degree in physics? You look for a job somewhere, right? He needed a roof over his head. He needed money. It's funny how he's exactly like my students. Dr. Carkner, I'm graduating. What am I going to do? I'm like, well, I guess you better get a job someplace. So Einstein got a job. He got a job at the Swiss Patent Office, right? It's a pretty famous thing. He was grading people's patents that they were sending in there. Well, this wasn't a very demanding job for Einstein, so he had some spare time, so he thought about physics. Physics was undergoing a revolution. This old model of Newtonian classical physics, where everything is very deterministic, where the universe is like a big machine, you pull the lever and something comes out the other side, that was starting to fall apart a little bit. Experiments and theories in the late 1800s were sort of casting doubt on that model. So he carefully went through these ideas, and he came up with a whole new model for physics. Note that he wasn't doing any experiments, he wasn't taking any data, he was just sitting in the patent office with his pencil writing these things out. But starting from a few simple postulates, he built up a whole new theory of physics. So I thought I'd talk a little bit about that. So let's talk about some of the ideas he had. Here's one of those ideas he had, special relativity. Relativity is the idea that things are different depending on your point of view. For example, if I'm standing still and you're moving, and we observe things, it might look different. So this is what Einstein's idea was. Let's say you're standing somewhere in a clock next to you, sort of like we have right down here. And then let's say you have another clock, and it's moving past you on a train, and it's moving. Clocks are identical, they're all mechanically sound, they all came from the same factory. You stand there for a while, the clock's driving around on a train, right? And then you compare the two clocks after a while. Is the time the same? Well, most of us would say yes, it's time. It doesn't vary. You know, if I don't go to the bathroom and come back and it's 20 years later, that would be crazy. Einstein said, nope, they're different. If you compare the two clocks, the clock on the train, each tick of that clock, it takes more time. And so what that means is less time passes on the train. If we get that train going fast enough, you can take a pair of twins. One could stand by the side of the road, the other could go around and around on a train, and the twins, when they came out, would be two different ages. Well, that's disturbing, right? Isn't time kind of supposed to be a thing that doesn't change? You can't mess around with it? And Einstein said, no, time is relative. You can calculate exactly how these different clocks are going to work. So that was a little bit weird. As Einstein was thinking about this idea, he realized he also needed to incorporate acceleration and gravity. So he asked himself the same question about the clocks. Let's say I have a clock that's floating in space somewhere. Every tick of that clock takes a certain amount of time. Then, let me take a gravitational object, a mass, a star or a planet or something, and let me put another clock on the surface of it. So the two clocks are separated. One's closer to a mass than another. We do the same thing. We let them run for a while, and then we compare them. Are they the same? Will they show the same time? And Einstein says, no, it's the same thing. The tick takes longer, and so there'll be fewer ticks, so less time passes near mass. If I live down at sea level, and you live up at the top of the mountain, different amounts of time pass for us. Again, what the heck, right? That's scary. If I go off and do something, and then I come back, maybe the time is going to be different. So this was a really radical thing. Unfortunately, Einstein worked it all out, but he realized he couldn't prove it. He didn't have a clock that was accurate enough. He couldn't get him going fast enough. But he had another idea about mass. And that idea has to do with the way in which mass distorts the fabric of space-time. This is also part of general relativity. If I have a mass, and I throw a mass near it like a ball, we know that it's going to curve, right? If I try to throw a ball straight, I can't do it. It's going to curve down towards the center of the Earth. Same thing is true if I have a beam of light. If I hold this beam horizontally, it won't stay horizontal. The Earth's gravity is bending this beam of light. The closer you are to the mass, the more bending there is of light. So just the way that mass bends the path of a baseball, it will also bend the path of a beam of light. Einstein was excited about this, but he also realized, I can't prove that either. I don't have sensitive enough instruments to do it. I can't set up a light beam here in the room and demonstrate and measure this small deflection. So the ideas of relativity were very interesting, but how do I test them? How do I verify them? Well, that enter our next hero here. That's Arthur Eddington. Eddington was British. He was also, like Einstein, very bright as a student. He went to Cambridge. Eddington and Einstein shared something. Einstein was an internationalist. He was a pacifist Jew. And Eddington was Quaker, but he was also internationalist. He was also a pacifist. So they had a similar political philosophy. Eddington eventually got a job, and his job was he was secretary of the Royal Astronomical Society. Now, in those days, secretary was a real job. You had papers coming in all over the place. You had to keep track of them all. During World War I, there was a lot of anti-German sentiment in Britain, and there wasn't a lot of contact with German scientists. Einstein's work was smuggled out of Germany and into the UK through neutral Holland, through a colleague of Einstein's, who we'll talk about more later, Willem de Sitter. And so these papers got to Eddington. Eddington, being pacifist, being internationalist, was less prejudiced against the Germans, was interested in the ideas, realized how radical, how revolutionary they were, and he became a big champion of Einstein's work. Eddington was trained as an astronomer. He had a lot of the same skills that you guys do. He could carefully use a telescope, make careful measurements. He was also trained as a mathematician. He was uniquely situated both to understand Einstein's work and also to test it. Eddington was part of a new breed. He was part of the astrophysicists. We're going to combine physics and astronomy together. He was one of the first people to really do that. So he began thinking about these ideas, talking about these ideas, spreading these ideas. How do we test the idea was a big question, right? Should we just expect people to believe us? This is a problem I have all the time. I'm standing up in front of you. I have a PhD. Well, I must be right. I mean, how could I be wrong? You wouldn't have brought me in here to speak. It's not a good idea. We should test everything. So they were trying to figure out a way both to expand on the ideas of Einstein, but also to lay an empirical groundwork for them. Someone who was instrumental in this was, in some sense, Eddington's boss. That was Frank Dyson. Frank Dyson was the Astronomer Royal, which I always liked that as a title, the Astronomer Royal, like the king would call him in. He'd explain whatever was going on in space to him. And Dyson thought about this, and he said, there's a way to test this. And the way to test this is to use an eclipse. I can't send a beam of light through a room, but a beam of light going through space past the sun, that would deflect enough for us to observe it. People tried this without very good results. Dyson says, we need to be serious about this. We need to put together a solid empirical grounding. We need to find an eclipse and test it. And he realized that the eclipse that was coming up in 1919 was going to be a perfect opportunity. So he, very nicely, I love this paper, he wrote it all up in the monthly notices of the Royal Astronomical Society, which is also a fantastic name for a journal, by the way. And he carefully, by hand, figured this all out. He said 1919 eclipse is going to have a long duration, 6 minutes. So that gives you plenty of time to take pictures. And just as importantly, the sun is going to go through a rich field of stars. It's going to go through the Hyades. And there's going to be lots of bright stars there that I can observe. I can't observe anything that's too faint. Specifically, take a look at these two little guys, which he numbered here by hand. That's the double star Capitoli, and both of its components going to get very close to the sun. They should deflect. They should be in a different position. You can measure that, and you can get very good data. So Dyson was very much on the right track for setting this up. Here is the star field that we're looking at. Here's the Hyades. The Hyades is best known here as being part of this V that makes up the face of Taurus and Bull. Right superimposed on it is the bright star Aldebaran. And then not too far from the Hyades over here is the Pleiades. And then right between them is where the sun's going to go, and there's Capitoli, who's one of our prime targets. So that's a great place to go through if you're not sure how faint you can go with your exposures. Unfortunately, there was a problem. There's always a problem. Problem with the eclipse? Well, here's the path. Right here, it's going to start in South America. It's going to end in Africa. But where's the prime point where you want to be? It's right in the middle of the Atlantic Ocean. Right? We all know this is true for solar eclipses. People say to me, "I heard there was a solar eclipse." I'm like, "Oh, it's in Antarctica. We're not going to see it in the Moline." So this was a bit of a problem. So they said, "Well, why don't we split our options? We'll send one team over here. We'll send one team over there. If we get bad weather or something, we can work things out." He had another problem. The guy who was supposed to be running this, Arthur Eddington, this was in the middle of World War I. They wanted to draft him, and they wanted to send him off to the Western Front. And so Dyson panicked. The guy who was going to make all this work was going to go get shot someplace. And so he managed to negotiate with the government, talk them out of sending Eddington off to the Western Front. He also scrounged a little bit of money out of the powers that be, and they set up this eclipse expedition. This was not a big priority for Britain during World War I, but Dyson managed to make it happen. One group went to Brazil. Eddington went to Africa, but actually just off the coast of Africa, this little tiny island here of Principe. Principe was under the control of Portugal, so it was a Portuguese colonial possession. And they exchanged letters of introduction and got some help from Portuguese colonial officials. Principe is mostly overgrown now, but at the time it was full of cocoa plantations. So this was where an awful lot of the world's chocolate came from at that time, was from this little island. It's known for eclipses and chocolate, which you think that's so important. So they managed to get there. They found a spot. It was in the middle of the wilderness. They had to have native bearers carry all their gear through the jungle in order to get it there. And they got things set up to make the observations. They had some problems as they were doing this. They had some cloudy weather. They had a strike of the steamship, so they almost couldn't get back home. But they did manage to get enough data. This is the equipment that was sent on the other side of the Atlantic to Brazil, and it kind of illustrates their setup. It's kind of unique. They didn't have their telescopes mounted. They put their telescopes in a shed. They built a little shed, and they stuck the telescopes in there. And then they directed the sunlight in this little celestat here. It was just a mirror that ran on a clock drive. It tracked the sun across the sky, and it shot the light of the sun through here, and then there were photographic plates in the back, and that's how they took the data. This was their big boy right here. This was a 16-inch telescope, and they brought that with them. But some of the astronomers said, I don't know if I trust it. It's got a little problems with the lens. Let's bring a backup. So they brought their backup. That's a 4-inch telescope. That telescope is this big. And so those are the two telescopes that they had in Brazil, and they had another telescope, and they just put the light through here. This was wound up like your old grandfather clock with a chain with a weight, and it put the sun in there. And that's how they made their observations. Now, back in those days, you had to do everything by hand, but today we have stellarium. So I fired up stellarium, and I pointed us to the island of Principe, and so this is what the eclipse would have looked like. It's much darker than the sky would have been. But here you can see the sun and the corona. Here you can see the V here of the Hyades. And if you zoom in a little bit, that's Capitoli. You can see how close it is to the sun. So I confirmed it. It was okay. I checked Dyson's work with stellarium. It seems okay. So it's so easy nowadays. I don't have to go to Africa or anything. And this is what they had. This was the data that they collected. So they took all these plates and packed them back up and took all their equipment and took it back to the UK. reduced their data, exposed to photographic plates, made careful measurements of the positions of the star, and they published their paper here in the publications of the Royal Society. They had some issues. That 16-inch telescope that they didn't quite trust, they were right not to trust it. It had a weird problem. It seemed to be heating up in the sun, and it was distorting the images. The images were kind of blurry, and it seemed like the scale of the images was changing. It was very hard for them to get good data with it. A lot of the data they used from that little 4-inch telescope, this little Mickey Mouse telescope. You can go on cloudy nights right now and buy a better telescope for like $100. And that's what they took a lot of the data with, was this tiny little thing. And they tried to figure out the sunlight, the light from the stars deflected by the sun, does it match Einstein's predictions? Einstein didn't just say, oh yeah, the light's going to deflect. He said exactly how it was going to deflect. Here's the pictures that they have. Here's their negative. You can see a couple of little stars right there. That's Capitoria again. You can see them up there in the picture. This was not some kind of CCD field that gets you down to 20th magnitude. This was whatever they could pick up on their photographic plate. They measured the deflection, and here's their data. This is their results. This solid line is Einstein's prediction, and this line here is the best fit to their data. Pretty close. They got very close to the value that they expected. So this was an excellent confirmation of Einstein's results. So Einstein wasn't just some crazy guy talking about clocks. He could make predictions, and this was just one of the predictions that he made that could be empirically verified. And Einstein said, you shouldn't believe me unless this data checks out. And the data checked out, and that's why we believe him. Well, this caused a big sensation. This was a big deal. It wasn't just scientists or the Royal Society. This got reported in the newspapers. It was something that ordinary people were interested in and talked about. Eddington promoted this. He went and gave talks and wrote popular books and articles. So this was something of general interest. This is a beautiful illustration in the London Illustrated News. I'm super impressed by this. He didn't even have Photoshop, the guy that did this. And it really explains the whole thing. I can just show you this picture. That's the path of the eclipse. This is the idea here. These stars are going to be at a different position, and the closer you are to the sun, well, then the more deflection there's going to be. And you can see a nice example here. This is where I see the star, but this is where the star actually is. And I'm looking at the sunlight here in my little observation. These are the headlines of the New York Times. I wish the New York Times would write headlines like these again. Lights all askew in the heavens. Men of science more or less agog over results of eclipse observation. When was the last time you saw the word agog? Einstein theory triumphs. So this was sort of the beginning, in some sense, of when you think of the guy who's the genius, it's Einstein. It wasn't just because he was a smart guy and we have to believe him because we don't want to admit that we're embarrassed that we don't get it. His predictions, results were right there. But it wasn't just a triumph. You can also look at it in a different way. People were nervous about this. If you read the line down here, stars not where they seemed or were calculated to be, but nobody need worry, right? When you look at the stars in the sky, they're supposed to be where they're supposed to be, right? The immutable heavens are supposed to be immutable. You don't go outside and look at the stars and say, where's that star? I don't know, it could be anywhere. It looks like it's there, but it could be somewhere else, right? That's disturbing. Maybe the universe is unsettling. Maybe things aren't where they're supposed to be. Maybe no one really knows where they're supposed to be. So some people were a little unnerved by these new ideas. One of the people, though, who were excited about him was a man named Karl Popper. Popper was a philosopher of science, a philosopher of politics. He became later known for books that he wrote, The Open Society and Its Enemies. But at the time of this experiment, he was a student at the University of Vienna. He was a philosophy student. He and his friends were debating and arguing over, well, philosophical things. The truth, right? What is right and what is wrong, and how do we know? Do we believe what people before us said? Do we believe the guy that has the most status? How do we know what's right and what's wrong? Well, later in his life, Popper would write about how Einstein's results affected him. What impressed me most was Einstein's own clear statement that he would regard his theory as untenable if it should fail in certain tests. Einstein didn't say, well, you better believe me or you're a bad person, or you better believe me or you're an idiot. He says, I understand that you don't believe me. I'm going to lay down all the tests that have to happen, and you can go check them for yourself. And so this had a big impact on Popper and his thinking. This is one of his most famous works, The Logic of Scientific Discovery. He says, the game of science is a principle without end. He who decides one day that scientific statements do not call for any further test, and that they can be regarded as finally verified, retires from the game. But Popper was also a political theorist, and political questions were very important then. We had this model of how we should run society, and it's collapsed. People have new models, the communists and fascists and many others. How do we decide how we run our society? Popper said, well, maybe we should subject everything to test. Maybe we should be a little bit leery about believing everything, and we should check stuff, and we should try to come up with a model where individuals have responsibility to figure out what's right or what's wrong. So this had a big effect not just on the scientific world, but also here on the philosophical and the political world. Popper viewed Einstein's ideas as a positive thing, right? We can make predictions, we can test them, we can have some confidence in them. But not everybody was in that category. This is H.P. Lovecraft, a famous writer. He's sometimes regarded as the father of American horror. And Lovecraft, well, he was afraid of everything. He was born into a well-off New England family. His family fell on hard times. He always kind of was worried about his standing in the world. And Lovecraft, when he looked at things, saw the horrible side of it. It was, in a weird way, kind of a gift. He was a brilliant writer for that. But he was also an avid amateur astronomer. He'd be right at home here. He'd be kind of creepy, but he'd be right at home here. He went to talks, he read books, he knew a lot about astronomy. If you've ever read any of Lovecraft's works, there's a lot of astronomy in them. He was affected by this and its various ways in which it was conveyed. This is Lovecraft's most famous line. The most merciful thing in the world, I think, is the inability of the human mind to correlate all its contents. We live on a placid island of ignorance in the midst of black seas of infinity, and it was not meant that we should voyage far. Most people say, well, astronomy, that's a very positive thing. It's the wonderful glory of the heavens is so beautiful. Lovecraft wasn't so sure. He's like, you look at that stuff and it freaks you out, right? We're small, we're insignificant. We live in a world and universe that doesn't care about us. Maybe a world and a universe that's stranger than we can imagine. If we think too much about it, maybe we'll be driven mad. So keep that in mind next time you're evangelizing astronomy. Well, back in those days, they didn't have any internet. So when you wanted to learn stuff, you had to read a book, or you had to go talk to somebody in person. And that's what Lovecraft did. This is Willem de Sitter. De Sitter was a colleague of Einstein's. He was the guy that helped get Einstein's papers out of Germany during World War I. De Sitter was a mathematician. He worked on the mathematical ideas of relativity. But he, like Eddington, was a popularizer. He gave talks, he wrote books, he tried to communicate science. And he had a lecture that he gave, it was called The Size of the Universe. And he gave sort of a tour in 1931, going out and talking about modern cosmology, explaining to people what our ideas were about the universe at that point. He published this in 1932. And here's a line from him. He says, we have realized that the mechanical model would not really mean anything beyond a slight help to our imagination. We are content when we succeed in representing the observed facts with a set of mathematical formulae. Normally, in our classical view of physics, everything is like a big machine, and we can kind of imagine a machine that would work. We've helped to understand physics. De Sitter's saying, maybe the machine isn't fundamental. Maybe the equations are fundamental. Maybe the equations in the math, in some sense, are more real than the mechanical model. That was this idea, and Lovecraft started to think about this. It's sort of like the fundamental truth is written in these equations, almost like a magical incantation that calls forth some powerful magic. The mathematics could be something similar. One of the ideas that underlied relativity that was disturbing was that Einstein realized that normal Euclidean geometry wasn't going to work. We needed non-Euclidean geometry. How many people here have ever taken geometry? Ever taken geometry? I took geometry, old-fashioned geometry, right? What do you do in geometry? What is the principal thing you do? Proofs,
tuggers.
right? It proofs. A implies B implies C. It's logically airtight. I have proved it. Here's a Euclidean problem. This is a triangle. What is the sum of all the angles of the triangle? 180. But maybe it's like 179. We're just rounding it up. No? Maybe it's really 180.1 and we just throw out the decimal? No, it's geometry. It's 180, right? It's set in stone. You don't disbelieve it. You don't debate it. You don't get into an argument. I'll give you a couple extra degrees. It's 180, right? It's something that we can count on. That's not true. Triangle doesn't have 180 degrees. Here's a triangle. It has 270 degrees. I got three right angles in my triangle. Weird, huh? It's on a sphere. If I draw a triangle on a sphere, it's a non-Euclidean space. All the rules of Euclidean geometry, they don't work, right? If I have two parallel lines, do they ever intersect? No, right? That's right there. If I put them on the sphere, whoop, they'll come together. How about distance? If I have a line segment, A, B, what's the distance between them? Well, the distance between them is the distance between them. What are you talking about? It's right there. You just measure it. But what if space is curved? What's the distance between these points? Is it the line segment? Or maybe are they closer together than they seem? So non-Euclidean geometry is necessary. In Einstein's model of mass warped space-time, you can't assume everything is flat. This freaked the heck out of Lovecraft. If you can't count on geometry, what can you count on? Right? If everything's open to debate, how many degrees are in this triangle? I don't know, it depends. We have to figure out this other stuff. That's really uncomfortable. Another big influence, it's our friend Arthur Eddington. Eddington was a big popularizer. He was kind of like the Neil deGrasse Tyson of his day. I used to say the Carl Sagan of his day, but now nobody knows who that is. And so he wrote books. He gave lectures. He was a super popular guy. He wrote this great book called The Nature of the Physical World. He tried to spell out for everyone, here's all this crazy stuff happening in physics. I'm going to explain it all to you, and then you'll know. Lovecraft read this book, and it got him thinking. Here are some lines from it. The external world of physics has thus become a world of shadows, Eddington says. If you look at quantum mechanics and some of these other modern physics ideas, again, they're not mechanical, they're not deterministic. You've got quantized particles, you've got clouds of probability, all these things that are very hard for our minds to grasp, and somehow they're producing the real world. Almost like the real thing is casting a shadow, and we're looking at the shadow, and it's hard for us to understand the real thing. Another line in here, he says, distances are linkages whose intrinsic nature is inscrutable. If you have non-Euclidean geometry, the whole idea of distance becomes kind of slippery. It's not entirely clear what we mean. So, and trying to explain these ideas of modern physics, Lovecraft began to get some ideas. He wrote a story combining these things together. It's called Dreams in the Witch House. It was published in Weird Tales in 1933, famous pulp magazine. And I like the sort of the subtitle of it. It's a story of mathematics, witchcraft, and Walpurgis Night. You normally think of those as being separate things. There's the mathematics, that's the reasonable, logical thing. And then there's a witch with a magic spell, and that's a crazy fantasy thing. And Lovecraft said, I'm not so sure. I think they might be pretty similar. And so he put them together in the story. This story really resonates with me. I don't know if it will resonate with you, but it's about a young man who's a student who's studying physics and math, and it's driving him insane. Anybody here ever studied physics and math? Does that seem about right? Yeah, it drives him insane. So I'm like, wow, I really get what he's talking about. And so in the story, our hero is lodging in an ancient house where a witch once lived, and there's all this folklore around it. He starts to have these strange dreams, and so it's a combination of these two things. Non-Euclidean calculus and quantum physics are enough to stretch any brain. And when one mixes them with folklore, one can hardly expect to be wholly free from mental tension. So he's taking these opposite things and he's putting them together. As the story goes on, our hero realizes these bizarre dreams that he has, maybe they're not dreams. Maybe he is really going to other places, to terrifying places. And as the story goes on, he begins to lose his mind. He begins to find himself in bizarre worlds that he can't comprehend. Had he actually slipped outside our sphere? Where, if anywhere, had he been? The roaring twilight abysses, the ultimate black vortex? To what extent do the laws of sanity apply? So, to Lovecraft, these new ideas were threatening. These new ideas were things that were maybe putting us towards a world that humans couldn't really accept or understand or comprehend. Maybe we're almost better off not knowing them and stay in our little world where everything is safe. It's interesting, or at least I think it's interesting, to contrast this story with a story by one of big influence on Lovecraft, and that's Lord Dunsany. Dunsany wrote a story in 1908 called The Ghosts, which I think is probably an influence on the Dreams in the Witch House. It's also about mathematics, but our hero here is plagued by spirits, and they're whispering to him, and they're urging him to murder his brother, or an irrational, terrible thing, and our hero tries to fight it. How does he fight the irrational things? He starts doing math in his head, right? But angle CEA is common, therefore AED equals CEB. The same way CEA equals DEB QED. It was proved. Logic and reason reestablished themselves in my mind. There were no dark hounds of sin. The tapestry chairs were empty. This is the traditional way we think about science and logic and math, and Lovecraft kind of twisted this around. So this was another way that people viewed the works of Einstein. Is it a positive optimistic thing that will cause us to invent a world where we test things and think about things logically? Or will it be something that drives us mad? Maybe the more we study the universe, the more we realize we have no place in it. Well, our heroes in our story went on to do other things. Albert Einstein, of course, won the Nobel Prize in 1921. This is Einstein giving his Nobel Prize lecture. Einstein, weirdly though, did not win the Nobel Prize for relativity. People were still not sure about relativity. He won the Nobel Prize for the photoelectric effect. When you have light, that light is quantized. It's not just an endless stream of energy. Individual photons, individual quanta of light strike a surface. If that photon does not have enough energy to eject an electron, the electron will stay put. If it does have enough energy, then the electron will leave. So the photoelectric effect is an important idea about quantum physics, and that's why he won the prize. Many physicists feel like this isn't quite right, or really a minor thing that Einstein did, won the prize, not his major thing, relativity. I'm not so sure. The photoelectric effect can be used in clever ways. You can make a little system where the light comes in and ejects electrons. You collect all those electrons, you figure out what the light was like, and you make a picture out of it. And that's what you have on your cell phone. If you have a cell phone with a camera on it, it's a photoelectric effect that makes that camera work. When you take a picture and you post it on the internet, well, you're using Einstein's work. This is the Nobel Prize for selfies that he won. That's pretty good. Right there. I should also say, if you're an astronomer, what do? Put a camera up on your telescope. You get fantastic images. You don't have to carry around a bunch of photographic plates like Eddington did. So for amateur astronomers, this is a pretty darn useful thing, the ability to gather up electrons that have been hit by photons. Eddington went on to also a long, successful career. A number of important ideas in astronomy come from Eddington. This is my favorite, the concept of the Eddington limit. How big can a star be? Turns out that there's It turns out that there's a limit to it that Eddington worked out. It goes like this. If you have a star, and matter is piling up on the star, it's increasing the pressure of the core, it's increasing the energy coming out of the star. That flux of energy coming out of the star is going to push new material away. As you make a star bigger and bigger, it gets harder to add more stuff onto it because it's going to get blown away by the energy produced by the stuff that's already there. This is a fundamental idea in stellar astrophysics. The limit to star size is about 100 or so times the mass of the sun. Bigger than that, you can't get any material close to it. Stars that are near that Eddington limit are unstable. They have a tendency to blow themselves apart. Here's maybe one of the most famous ones. This is Eta Carina, a very famous nebula. There's a pair of stars in here, and they're at this Eddington limit, and they're constantly blowing off their outer layers, and material is coming out of them. So that's an important contribution to astronomy. Well, I want to go back to one more thing from H.P. Lovecraft. Lovecraft's interest in astronomy was something that lasted throughout his life. And while this expedition was going on, while the eclipses were being photographed, Lovecraft was writing a story called Beyond the Wall of Sleep. In this story, a doctor is trying to cure a madman. Can't quite understand what this guy is saying. He eventually finds a way to go into his dreams and finds out this madman is actually an alien. And he's going to be leaving our planet. He's going to do battle. He's going to use cosmic forces to do battle someplace else in the galaxy. And he tells our hero, look to the sky, you'll see the signs of my struggle. And up in the sky, the people of Earth saw a bright new star, and that was Nova Persei. That was a real nova that occurred in 1901 when Lovecraft was a young boy, and he remembered this event. This was one of the brightest naked-eye novas that had happened in the early 20th century. If you look in the sky where that occurred, you'll see what's called fireworks nebula, and this is the remains of that explosion. Nova Persei is what's called cataclysmic variable. Material builds up on a white dwarf, and then it explodes outwards. And so that's another astrophysical connection for H.P. Lovecraft. So here is a picture that I found that shows some of our key figures. Here's Albert Einstein. Over here is Willem de Sitter. And over there is Arthur Eddington. I couldn't find one with both Karl Popper and H.P. Lovecraft. That would be pretty exciting. I was going to Photoshop them in, but I said, no, we don't want to get you carried away. This is in De Sitter's office in the Netherlands. And whenever you see these pictures, and I said, who's the famous people in these pictures? Well, maybe if you're some kind of weirdo, you recognize Willem de Sitter or Arthur Eddington. But is there anybody that wouldn't recognize Einstein? Einstein is almost more famous as a cartoon character than he is as a scientist. If you Google Albert Einstein, you get stuff like Albert Einstein, was he the smartest man in the world? Albert Einstein, what was his IQ? Right? He's kind of a pop culture figure. We forget what was important about Einstein. His contribution to physics, yes, but I think it was more than that. It was the fact that he always insisted all of my ideas should be tested. Whatever I come up with, whatever theories I have, maybe they all seem really good here on this piece of paper in the patent office, but we should only really accept them if they can pass these tests. Note that we're not stopping with that. This is a recent photograph from the Grand Telescope at the Canary Islands, and this is an Einstein cross. Light is bent by masses. If you have a big enough mass, like a galaxy or a cluster of galaxy, then it can actually take objects behind it, bend the light to you, and create an image. In this case, it creates 4 images. A, B, C, and D are all the same background galaxy whose light has been bent around the foreground galaxy. And this is another example of gravitational lensing. So we are still testing Einstein's idea. This is just from about a month ago. So Einstein said that his work should be tested, and we take him at his word, and we physicists today. We haven't stopped. The work that Eddington began in 1919 is still continuing today. So what I always say is, I'm currently conducting an experiment which may prove Einstein wrong. Ooh, exciting. It's impossible to find a good sandwich in this town. So Einstein would have wanted us to test his work. So go out there and test Einstein's idea, whether it's observing something with your telescope or maybe just seeing if you can get a decent sandwich in Princeton. And I'll leave you with that. Thank you. If you guys have some questions, I can take some questions. You have a question back there?
No. Stepping back to Einstein's cross, which is so crazy. Why are those discrete points instead of a ring?
So you may be familiar with the idea of an Einstein ring. And the Einstein ring is if you get everything lined up perfectly. If you have a perfect alignment, then it'll actually be bent completely around in a circle. And it's because the alignment isn't quite right that we don't get a ring. The masses are not point masses, and their alignment is not quite exact. So we see a lot of different effects of gravitational lensing, and you can get closer and closer to one that's lined up perfectly, but it's hard to find one that's lined up really straight. So something like a cross is more common where you get little bits of the ring, but not the whole thing.
Those are not complete images, each in its own.
Yes, each one is, but you could get them to go around in a ring if the system was ideal, but it's not. Oh, do you have a microphone? Oh, do you have a question for that? This is like Oprah.
So you have a great context of history. One of my favorite physicists of the past was Vera Rubin. Could you comment on her place of significance? Like Einstein had photoelectric effect. I just am sad that Vera Rubin died before she could get a Nobel.
Oh, me too. I used to put money on her every year. Sure, I've met Vera Rubin. I've heard her speak. Vera Rubin was one of the principal people responsible for ideas about the dark matter. Back in the 70s, Vera Rubin and her team were looking at galaxies and watching them rotate and doing spectroscopic studies of them. And what they kept finding was they were rotating too fast. If you looked at the galaxy and you saw how much mass it looked like it had, it wasn't enough to hold the stars on. They should be flying out into space. She reported the results, and people thought she was crazy. They were like, Vera, maybe go try again. Obviously, the galaxy can't have missing mass. It'd have to be some sort of, dark matter that was responsible. Well, she kept doing it, and she kept getting the same result. And so that's why we think about dark matter the way we do, is because galaxies are missing mass. If you add up all the light, no matter how you find it, it's not enough to account for it. So that's Vera Rubin. Vera Rubin's place, of course, was many years after these.
Yeah, could you speak to the controversy of Eddington's measurement when he? If you could throw that slide on there,
Sure. Yeah. Well, I don't know. I feel like. Can I go back fast enough? I'm not sure about the controversy of it. I think it's actually pretty straightforward.